Let's tackle now one of the biggest and most interesting results of the special theory of relativity, and that is time dilation. Um, we saw in the last video on simultaneity that time is no longer a constant. Time now becomes a variable, and we're going to deal with it as a variable here in this section. Let me show you how. So here's an interesting thought experiment to help us understand time dilation. So you have a clock that is based on light. So you have light from some source, it moves across a device, hits a mirror, and then comes back and impacts a receiver. And then you have a clock timer that records that amount of time. We're going to use this clock in two scenarios. In the top, you just see that clock just holding still. But on the bottom, that clock is now moving forward at some velocity v. Okay, let's take a look at just the clock that is holding still. In other words, it is within your inertial reference frame. Well, how fast is the light going? Well, velocity is distance over change in time. The speed is going to be the speed of light. How far did it move? Well, the clock has a distance d, and so it had to go across that distance d, and the light had to come back. So the distance the light traveled is 2d. And now we're going to define our time. We're going to call this delta t naught, also known as the proper time, or time within the inertial reference frame. So you sitting there inside that clock, you time how long it takes for the light to pass, and you calculate delta t naught, the proper time. Okay, so we are going to solve for the distance d. This will come in helpful in the next couple slides. So if we solve for d, then that would be speed of light times the proper time, but then we have to divide by 2. Okay, so remember this, that the distance across is going to be 1/2 of the speed of light times the proper time, where the proper time is the time it took for the light to go across and back to the receiver. Okay, now we're going to consider the same timer as it moves forward at some velocity v. Okay, but now you have your light source here. By the time it reaches the mirror's over here, and then bounces back and hits the receiver when it's over here. Okay. So again, velocity is equal to change in position over change in time. There are now two velocity equations that we need to look at. One is the velocity of the timer, and two is the speed of the light itself. So the velocity is going to be, well, some distance. It goes this distance L twice, and then it goes over some time. We're going to call that delta t, where delta t, well, I'll talk about delta t in just a second. Okay, the other thing we need to consider is the speed of the light itself. So the speed of light will be distance over time. And time is the same as what we just saw, but the distance is now different because now it has to travel this path right here. And how do we calculate that path? Well, we create a right triangle, this leg is distance L, this leg is distance D. Using Pythagorean theorem, we get that each leg is square root of D squared plus L squared. But it has to do two legs, to the mirror and then back to the receiver. So it's 2 times the square root of D squared plus L squared. Now, we're going to get rid of the square root. And so we're just going to call that C squared equals 4 times D squared plus L squared over the change in time squared. So we just squared everything. All right. Now let's get rid of the fraction. Let's go, sorry, let me do it this way. C squared times the change in time squared is going to be 4 times the distance squared plus L squared. Well, D, we solved in the last slide. Remember that D is equal to 1/2 C times the proper time. So if we square that, we get 1/4 C squared times the proper time squared plus L. Well, we can get L from here. If we solve for L, then that'd be velocity times the change in time, but then that would equal 2L, so we have to divide by 2. That gives us a 1/2. And that, so we have to square that, so that would be 1/4 V squared delta T squared. Now we need to keep track of the delta T's and the delta T naughts. Okay, so if I simplify this, you have some quarters, but then you multiply everything by 4. So this becomes C squared times delta T squared has to equal C squared times the proper time squared plus V squared times delta T squared. Okay, now we are going to solve for delta T, which if I do that, I'll move this term to the other side and factor out. So delta T squared times C squared minus V squared has to equal C squared delta T naught squared. Okay, so let's carry this on forward. Let me just rewrite that right here. So we said that delta T squared times C squared minus V squared, make sure I got that right, has to equal C squared times the proper time squared. Okay, let's divide everything by C squared. And so we get that the proper time squared has to equal delta T squared times 1 minus V squared over C squared. Now I have to divide by that factor. And then finally take a square root. And this equation right here is known as the time dilation equation. So what on earth are we talking about with this equation? This is weird. Okay, here's what's happening. Inside of the clock, you have a certain amount of time happening between ticks, so to speak, within the clock. But you, as this observer outside in a different inertial reference frame than this clock, you have this interesting factor going on at the bottom, which then gives you a different amount of time. So the amount of time actually passing within the clock is different than the amount of time passing for someone in a different inertial reference frame. Weird. So time is no longer a constant. Time changes based on your inertial reference frame. So no longer can we use time as a constant unit of measure. We used to deal with 3 dimensions, which is changes in x, y, and z. But now we have a 4th variable that we have to deal with. And this is where the 4th dimension idea comes from, where you have to deal with changes in space and changes in time. Time is now a variable that we have to deal with.